All right, I'm helping you get a lab started and explained. So we have a lab. We're going to do it in Pivot, but we're going to learn about how we would have done it in the classroom, and this is my approach. So here's my lab number 2. Fan car force versus acceleration. So let's look at the objective. Student has an apparatus that allows a student to apply a force to a cart with an unknown mass. Okay, we're going to assume the mass is unknown, even though you're going to pick a mass for the cart. Design an experiment to determine the inertial mass of a system, and I call it a system because it's a cart and a fan, using Newton's second law. So there's the objective. I want to design an experiment to determine the inertial mass, and I have given you the physics principle. And I'm telling you the first step you need to do is find a math model. Find an equation that contains the item that we're trying to find, which is inertial mass, and I've given you the physics principle. Okay, so let's write Newton's second law. I know that force is equal to mass times acceleration. Okay, and what am I trying to find? I'm trying to find mass. I'm trying to determine the mass of something. So rearrange that equation where I have mass is equal to force over acceleration. And then ask yourself, in that equation, that math model, is there something that I can measure? Are there variables that I can measure? Well, there's only 2 variables, so this one's actually pretty straightforward. The variables are force and acceleration. And to be honest, it's actually not that difficult to measure a force. Okay, we have actual force sensors. So if I have a sensor that I have a certain type of pressure that I put on an object, I can see versus my sensor, I can actually measure the force electronically. Another type of tool that we use to measure force is called a spring. Well, it's a spring, and springs actually have characteristics that you're going to learn about. And a scale that you stand on is actually a spring scale. 99% of them are. At any rate, so we can actually measure the force, and you've learned how to measure an acceleration of an object, right? Acceleration, if I know, let's say I have change in x, bi time plus 1/2 at squared. If I can get a situation where initial velocity is 0, and I can measure the time and the change in distance, I can find acceleration experimentally as well. So those are 2 variables that I can actually do in the lab. I can measure a force, and I can measure an acceleration of an object if I have some data about the object's motion. Okay. All right. Now I want to just talk a little bit about graphing. So if I have y equals mx plus b, and I'm just going to assume that b is 0. We're going to disregard b for just a minute, and I'm just going to look at y equals mx. That is a linear relationship with a constant slope m. That is linear. That follows the definition of a linear relationship. I'm going to rearrange that equation for slope. So y over x equals m. All right. So if I have something on the y-axis and I graph it to if I graph a variable and place it on the y-axis versus another variable and put that on the x-axis, and it has a linear relationship, whatever is on my y and whatever is on my okay, what am I trying to say? I can use this relationship and find the slope to be equal to something. Okay, let's see what I'm trying to say. All right, this is constant. Okay, that's the because we have a linear relationship. So just based on this equation right here, the mass is a constant item. It's not changing. Okay, so if I were to take some force measurements, say I put a force of 1 Newton on it and measure the acceleration, and then I put 2 Newtons on it and measured the acceleration and plot that data, I can find the slope, and that slope would be equal to that mass. Okay. The trick that I use to kind of figure out what to graph to determine whatever experiment, I know I find what I want on the y-axis. It's got to be on the top. Slope is rise over run. And I graph what I'm looking, another variable on the x-axis. and then I can figure out what the slope is, because it's not always going to be one thing over here to the left. Okay, we'll do some more, don't worry. Now, what if I graphed acceleration versus force? Well, what's on the y-axis? Acceleration. What's on the x-axis? Force. And what is that equal to? 1 over m. So now, once I find that slope, so there's my slope. Let's just call it slope so I don't throw in another variable that looks like what we're doing. I know that that slope is equal to 1 over m. And I can find m by taking the inverse of the slope. Okay. All right, continuing on. So based on my original math model, what are my variables? Well, I have force and I have acceleration. Okay. Now, it's really useful to identify independent and dependent. We're going to change the force because it's easy to do in this experiment. So that is my independent variable. And we're going to measure this. And that is my dependent. It's dependent on how much force I put on it. Okay. Now I'm going to do a little quick sketch about what the system looks like. So I have a spring that has a ring on it. And I have a cart that has a fan on it that sits on a track that is frictionless. And there's a string that's attached to that that I can cut. Okay. And this picture we'll assume is right before I cut it. So the fan is on. The spring would have been, when I had the fan off, would have been stretched maybe just to there. Okay, because then when I turn the fan on, the spring gets stretched, but it holds the fan. And then I cut the string. This is a string or a ribbon. I'm going to cut it and the fan's going to take off. The cart and the fan is going to take off. And by the way, it has an initial velocity of 0. And then I'm going to go sum delta x, and I'm going to measure how much time it takes to go that delta x. All right. Right before I cut the string, I want to show the forces. I'm going to call it a free body diagram. So FBD is my free body diagram. This is the free body diagram before I cut the string. So I have a force pushing up on the fan system by the table. We call that, or the track, that's force normal. I have the force of gravity, which is acting down on the fan and the cart, because you just learned about it. The fan is actually putting a force applied. That's a driving force. It's trying to push that fan to the right. What's holding it there? Well, the force of the spring is pulling it back to the left. I know you haven't learned about spring forces, but it's sitting there ready to go. It's stretched the string and it's holding it there. The only thing that's holding that fan cart system there is the string, because as soon as you cut the string, it's going to take off, and that spring is pulling it. It's pulling backwards, and its acceleration is 0 at that moment, right? Its acceleration is 0 right here, because why? Because the forces in the x direction are equal to the forces in the y direction. That force that spring applies to that fan cart system, it's equal to the force applied by the fan. So I know that the forces in the x direction have to equal 0 because it's sitting there, because it has 0 acceleration, and I can say that that is equal to the force applied by the fan, which is my power, that's my source of, minus the force of the spring, because the spring is to the left, and then those are equal to 0 when I add them up. So let's actually make it even more clear for you. I'm going to add the negative force of the spring, right? Because it's pushing to the left. And those now are equal to one another because I can set that equal to 0. All right. So if I can measure the force of the spring, then I know the force that the fan puts on. So then I can change the force. I can change the speed of the fan. The higher the speed, the longer the string is going to stretch and the more the force that it's going to put on it. So one last thing. As the fan and the cart is moving, and as it's moving, because now it's taken off, I want to draw the free body diagram in that situation. I still have my force normal, that's the pushing upwards on the cart from the track. I still have force of gravity. The fan is still on, but the spring is no longer a part of the equation because we cut the string and now it took off. And notice, I do not have 0 forces in the x direction anymore. I have the force in the x direction, which is equal to Fa, and that is no longer a 0 force in the x direction, and that will be equal to the mass of that system times the acceleration. So whatever that value is, newtons, I can then record that data, right? I know now that that's what's causing the acceleration. Okay, so there's the 2 free body diagrams before I cut the string and after I cut the string. All right, moving on. What kind of equipment do I have? Fan cart. Cart with wheels, high speed fan on it. The larger it goes, the more force it puts on it. I have a track, and it's assumed to be frictionless. I have a meter stick, but on pivot, we'll use a ruler, the calibrated ruler. I have a force sensor, but in pivot, we have to use a ruler that's been calibrated to measure the force. By the way, we do have spring scales in our lab, and a stopwatch, which we have a timer. We are going to select the system with an unknown mass, but you're going to pick a mass. Set the fan to the lowest setting using the force sensor that they give you. Measure the forces exerted on the system when at equilibrium. Measure the time it takes for the system to travel a known distance. Record the time and distance in the table. Using kinematics, calculate the acceleration and record that in the data table. Repeat this so you're going to have force 1, force 2, force 3, force 4, force 5. So you're going to have 5 rows of data. I think there's 5 settings on the fan. Then you're going to graph. They want you to graph the dependent variable versus independent variable. So you're going to graph acceleration versus force. Okay. And A over F is equal to 1 over M. So that's what your slope is equal to. 1 over the inertial mass. So find your slope and then take the inverse of it when you want to know the mass. Okay. Make sure you plot your best fit line using pivot. All right. What are the instructions in pivot? It'll have a get started section. It's just familiarizing with all of your equipment. You're not actually doing your experiment. Then you're into collecting your data. Okay. They're essentially marching you through exactly what I just did. They're going to tell you, and actually I added some words in there, so you'll see. Set your data table and create your graph. Make sure you have all of your things labeled: force, distance, time, and acceleration. Super important. Somewhere you have to convert from centimeters to meters. I would do it in where I do my acceleration calculation. Okay, so you're going to have a column where you actually input a formula, and you can just have your formula to convert from centimeters to meters. So the units in your acceleration column should be in meters per second squared. That's good. You will receive reduction in points, by the way, if your units are wrong. Label the graph. Always label your graph. Title, x-axis, y-axis. Make sure you add a curve fit. They give you a little video if you need a refresher on how to use data tables and graphing. They tell you in that video how to turn that uncertainty feature off. So when you do a best fit line, you know how it had plus and minus and everybody was all confused about that? You can actually turn that off. We don't need it. That'll make your data look a little bit easier. Again, I'm telling you, you're going to be graphing acceleration versus force per the recommendation, which again, I don't really think that it matters in science back in the day, or what we do in the lab. We make it so that the graph gives me a linear relationship, that the slope is as close to what I'm looking for as possible. Let's see. At the very end, I will ask the question, how does your experimentally measured mass, so that's going to be related to your slope, you're going to use the slope of your data to find that experimentally measured mass, compare to the mass that you selected in the original part of the lab? Do some research. Tell me how to calculate percent error. That would really impress me. So you may have, let's say you selected 800 grams and you came out with 1,000 grams, or maybe you came out with 1,500 grams. Why? What's your idea? Because nothing ever comes out perfect. I have an idea actually why there might be error. I'm not going to tell you. Okay. That's what I got. I don't have any problem with you getting together with one of your friends on FaceTime and working on this lab as a group teamwork. I have no problem with that at all. In fact, I almost assigned it as a group project, and I plan on doing that in the future. But I'm going to let you decide that. So get your friends online, pick a mass, work through it together. That's what I got.